So we are trying to find the area of a surface of a certain z function, z equals x squared plus y squared, between the planes z equals 5 and z equals 7. So because it's a surface area problem, we're going to use this formula. The integral of a region plus is the square root of 1 plus the partial of x squared plus the partial of y squared and the region of dA. So the first thing we need to do is find the partials of our function. So the partial of x, the partial in respect to x is 2x. The partial in respect to y is 2y. And so once we have this, we're going to leave the rectangular region, the limits, undefined for now, because we're going to have to switch this to polar later on, as you'll see, because it'll make the integration much easier. So let's rewrite our integral and plug in our partials. Alright, so this integral is going to be pretty gnarly to do without converting to polar. So if we look over here to our handy-dandy diagram, you can actually, you'll see that these, the sort of shadows of the parabola where z equals 5 and z equals 7, they actually make some circles on the xy plane, which I will draw right here. So at z equals 5, it'll make this shadow right here. And so the radius of that will actually be z equals x squared plus y squared. If we plug in z equals 5, we can come out with an equation for r. And we know x squared plus y squared equals r squared, so we can convert this to polar and get the radius. The shadow of z equals 5, its radius right here is root 5. And if we do the same thing for the outer one, we can see that it'll be root 7. So these are our two shadows, and we will use them for our limits of our integration after we convert the integral to polar. So in order to convert the rest of this to polar, we know x equals r cosine theta, y is our sine theta, and our dA will become r dr d theta. Okay, so now that we know this, we know our limits. Oh, and we need to find our theta limits, and we know from this would be 0, and to go all the way around, we have to, in polar, we have to do theta from 0 to theta to 2 pi. So these will become our new limits, 0 and 2 pi for theta, and root 5 to root 7 for the radius. And so now we can convert everything to polar. So let's do that really quick. 1 plus 2 cosine theta squared plus 2r sine theta squared r dr d theta. So our limits of r are root 5 to root 7, and our limits of theta are 0 to 2 pi. Now here, because we have no thetas, or because we have, just a second. First we need to evaluate this, and you'll see in a second that we will remove the thetas because of the Pythagorean property. So let's evaluate that really quick. 1 plus 4r squared cosine squared of theta plus sine squared theta. Alright, so we know that this is equal to 1, so we can remove that and we're left with 0 to 2 pi. Let me just 5 to root 7. So now that we removed all thetas from the integral, we can actually split this because all we have is d theta, and we have this integral with r has no thetas in it, so theta is basically constant. So we can just split this integral into 2 parts. Okay, so from here, it's a easy integration. This is just 2 pi minus 0, which I'm sure you can do. And then this one, this is actually just a simple u substitution, and our u would be 1 plus 4r squared. Our du would be 8r. And so we don't have the 8 here, so 8r dr. So 1/8 du would equal r dr. And so I will skip converting all the limits to u, but what it'll basically look like is 1/8 root 5 to root 7, 8r, 1 plus 4r squared, dr. So from here we can just do the integral because we know this is the derivative of that. So we will get 1 plus 4r squared to the 3 halves and times 2/3. And this is from root 7 to root 5, and this is just 2 pi. So now we can evaluate this, and what you'll end up getting is pi over 6, 29 to the 3 halves, minus 21 to the 3 halves. And that is your answer. And so this is the surface area of this paraboloid, which is defined by that equation, and from z equals 5 to z equals 7.